Hey, all you software engineers out there, get ready, because today we're diving deep into a paper that's going to speak directly to you. It's called Titans, Learning to Memorize at Test Time. And let me tell you, this is one you'll want to keep handy.
You got that right. This paper dives headfirst into a challenge we all know too well. Dealing with those long and complex sequences of data. We're talking massive code bases, huge data sets, you name it, even with all their power. Transformers can hit a wall when things get too lengthy.
Kind of like trying to run some super intense application, but your system's RAM is maxed out, right? Everything slows to a crawl, and nothing works the way it should.
You nailed it. That's a perfect analogy. And that's where Titans come in. They're built to handle those massive sequences. And they do it with a pretty smart approach to memory, one that takes a page from how we as software engineers think about memory in our own systems.
Okay, you've definitely piqued my interest. Let's unpack this problem a bit more.
Hmm.
Why exactly are these long sequences such a pain for the traditional models?
Well, you've got two main suspects. On the one hand are your classic transformers. Powerful, no doubt. But they've got this thing called quadratic complexity. As the sequence length grows, the resources they need, well, they skyrocket. It's like you're trying to cram a terabyte file into memory. Sooner or later, you just run out of space.
And then there are the simpler linear recurrent models. What's their deal?
They're all about compression, trying to squeeze all that info into a fixed memory. Problem is, you can't avoid information loss. It's like summarizing a whole code library into a single variable. You're bound to miss some vital details.
A classic trade-off then, power versus efficiency. Transformers are strong, but they're resource hogs. Linear recurrent models are light, but they're forgetful. So where do Titans fit into all of this?
Titans are all about balance. Taking cues from software architecture, they treat different parts of the neural network as separate memory systems. You've got your attention mechanism, which is like short-term memory, good for the immediate stuff, but limited in what it can hold. And then there's this new concept they bring to the table, neural long-term memory.
Now, as a software engineer myself, I'm always curious about structure. How does this long-term memory thing actually work?
It's based on a pretty neat idea, learning from surprise. Think about debugging code. You hit some unexpected behavior. It grabs your attention, right? It sticks in your mind because it breaks the pattern.
Makes sense.
So,
It's like stumbling on an edge case you totally didn't see coming.
precisely. So the model figures out a surprise metric. It uses gradients to see how much an event strays from the norm. And if something is surprising enough, bam, it gets stored in long-term memory.
Like a dynamic priority queue for memory, the most surprising events get pushed to the top. But even in a neural network, memory has its limits. What happens when that long-term memory starts to fill up?
They've got that covered too. They use a forgetting mechanism. Kind of like how we manage memory in our own systems. It's all about decay. Information that's been sitting around unused gets nudged out, making space for the new stuff, the potentially more relevant stuff.
Like garbage collection for the neural network, keeping things tidy and optimized. I like it.
And this is where it gets really interesting. This isn't just memorizing the training data. It's about learning how to memorize right there at test time. A meta-learning approach, if you will.
Hold on, so it's not just storing facts, it's learning how to learn.
Exactly. And that's key for generalization. It means the model can handle new data stuff it's never seen before, just like a seasoned software engineer can tackle new problems with their existing knowledge.
Okay, now that's impressive. So we've got these separate memory systems working together, but the paper talks about different Titan architectures, MSI-MAG and MEML. What's the story with those?
Think of them as different ways to connect these short-term and long-term memory systems. Kind of like different design patterns in software. You've got your options, each with their own strengths and trade-offs.
Okay, so walk me through these Titan architectures. I'm all about different design patterns, especially when it comes to something as fundamental as memory management.
Sure, let's start with MMAC, which stands for Memory as Context. It's kind of like making a targeted request to that long-term memory based on what's happening right now. Think of it like calling a function in your code. You give it some input, and it fetches the relevant info from memory.
So it's a focused retrieval mechanism. What about MAG?
MAG stands for Memory as Gating, and it takes a different route. It mixes the outputs of both the short-term and the long-term memory, kind of like how a program might use both RAM and a hard drive for different data access needs.
So it's like a hybrid approach,
Yeah.
blending speed and capacity. Interesting. And what about the last one, ML?
MEL stands for Memory as Layer, and it's all about preprocessing. It uses that long-term memory to refine the data before it even gets to the attention mechanism. Kind of like a cache that speeds up data access, like having a smart index for your memory so you can find what you need in a snap.
So each architecture has its own way of working with that long-term memory. It's like choosing the right data structure for your algorithm. They all have their own performance quirks. But how do these titans actually perform in the real world? As software engineers, we're all about results.
Absolutely, and the results are pretty impressive. The paper puts Titans through their paces with some tough tests, and they consistently outperform other cutting-edge models, especially when it comes to those long, challenging sequences we talked about.
What kind of tasks are we talking about here? Give us some concrete examples.
Well, for one, they're really good at language modeling. They can predict the next word in a sequence with amazing accuracy. And that's super useful for things like code completion documentation generation, even stuff like code summarization.
Like a turbocharged autocomplete that gets your whole code base. That's pretty neat. What about tasks that are more than just predicting the next word, though? Tasks that need an understanding of the code's logic and structure.
You're talking about searching a massive code base for a specific function or understanding what a piece of code is supposed to do right. That's where the needle in a haystack task comes in. We call it NIAH for short.
NIAH, that sounds like a real challenge.
It is. NIAH is designed to see how well a model can handle long contexts and pick out specific bits of information. And guess what? Titans, particularly the MAC variant, aced it. They blew the competition away. They even conquered a particularly tough benchmark called Babylon.
So they can find that one function definition hiding in thousands of lines of code. Impressive. You mentioned earlier that Titans are being used in fields beyond software engineering too, like genomics and time series analysis. What do those results look like?
Just to show how flexible this approach is, Titans are doing great in those areas too. In genomics, they're being used for things like predicting what a gene does and spotting mutations. And in time series analysis, they're proving to be really good at forecasting trends, like stock prices or weather patterns.
Okay, so whether it's code DNA sequences or market trends, Titans are proving their worth. But I keep hearing you say deep memory. What's so special about deep memory in this context?
It's all about representation. A deep memory, which is essentially a multi-layer neural network, can create much richer and more nuanced representations of information, compared to something simple like a matrix or a vector.
As software engineers, we know the importance of choosing the right data structures. So a deep memory is like going from a simple array to a full-blown graph database.
That's a great way to put it. A deep memory allows for more complex relationships and connections between pieces of information, making it much easier to store and retrieve knowledge effectively. And the paper shows clearly that deeper memory leads to better performance, especially on those long sequences that give other models trouble.
So it's this combo of separate memory systems, a deep memory structure, and the ability to learn how to memorize. That's what gives Titans their edge.
Exactly. It's a potent mix that opens up a ton of possibilities for AI applications.
You know, we're focusing on software engineering here, but I can't help but think about the bigger picture. We've talked genomics and time series analysis. But what about other areas where AI could benefit from this kind of robust long-term memory?
You're right on the money. Think about areas like natural language processing, where understanding the context of a whole conversation or document is crucial. Or in robotics, where a robot could learn from what it's done before and adapt to new environments more effectively. The potential is huge.
And let's not forget about the ethical side of things. As we build these more advanced AI systems that can learn and remember on this scale, we have to make sure they're aligned with our values and goals.
Absolutely. As we push AI further, we need to be aware of what could go wrong and make sure we're developing these technologies responsibly.
All right, we've covered a lot today. We've looked at the challenges of handling long sequences, dug into the architecture of Titans and their clever approach to memory, and even touched on the broader societal implications. But before we wrap up, I want to bring it back to what matters most to our listeners, their work as software engineers. Imagine this. You've got a code assistant that doesn't just finish your line. It gets your whole project's history, the ins and outs of how you code. And it can even spot potential issues based on past hiccups. That's the kind of power we're talking about.
It's like moving past those AI systems that felt like they had a memory problem. Remember those old rule-based systems?
Yeah, we tried to cram all our knowledge into them, but it never really worked.
Too rigid, too fragile. The real world's a messy place. You
Yeah.
can't plan for everything.
That's what's so cool about this neural long-term memory approach. It's not about hard-coding every rule. It learns the principles of how information is structured and retrieved. It's like teaching a model to think like a software engineer, to build its own intuition about how software ticks.
You got it. It's not about memorizing a bunch of facts. It's about understanding a world that's always changing. What if it could remember every line of code you've ever written? What if it could learn best practices from millions of open source projects? or even predict your next move based on your coding style.
Now, that's a code assistant I'd sign up for. So if you could build the ultimate code assistant, what would long-term memory look like in that? What amazing things could it pull off? Share your ideas with us online. Hit us up on social media, leave a comment wherever you hang out. We'll keep diving into the latest AI breakthroughs that matter to you. Until next time, happy coding.